Hey folks, today we're going to talk about Rust lifetimes. If you're a Rust beginner, you may not have seen them yet, and they'll be tricky, and I'd like to help you get ready for them. If you have seen lifetimes before, I still want to come back to an example of what we might see for the first time and talk about how to fix it, which you might already know, but also think about how the compiler sees the code and how, when we fix it, what are we telling the compiler? Why does it need to know that? So I want to try to think like the compiler as we fix the code. That's what I want to do here. I'm doing the same thing I did in a previous talk where I'm going to record it twice. So this is the slow version. I'm going to go much more slowly here. And then I'm going to record a fast version. So if you have already seen lifetimes before, you might want to start with the fast version. Or you can reference back and forth as needed. If you haven't written any Rust before, this will be pretty aggressive. There's going to be a lot of material here. But if you want to try it, you might want to try it here with the slow version. This is the slow version. So here we go. Here's some code. What does it do? Let's look through it briefly and run it. And then we'll go through line by line because, again, this is the slow version. And I want folks who haven't written any Rust to have a chance here. So we create a string. We put that string in a vec, a list. That is to say, we push a reference to the string into a list. This is a comment. We don't do that. We print the list. Okay, so we have a list containing a reference or pointer to a string, and we print it. Let's run that. Okay, a list of one string. So nothing very exciting here. Let's go line by line to give everybody a shot, even folks who haven't written Rust yet. So capital S string, if you're coming from C++, very similar to standard string, right? If you're not coming from C++, this is a little bit less familiar. This is a string that owns the memory that holds its characters. So when this string goes out of scope, at the end of the function, that memory gets freed. That may be new. That's okay. So this is a capital S string. If you've seen lowercase stir in Rust, that's a reference to characters that someone else owns. This is the version that owns its memory. Vec, like standard vector in C++, if you've seen that, it is a growable list, right? Here I've said the type of the vec. You don't usually need to do this. We don't even necessarily need to do this here. It'll help later as I comment some stuff out. It'll help us avoid some errors. I've gone ahead and said what the type is. And then we push into the vec, we append. This is a reference, a shared reference is what Rust calls this. It's like a const pointer. It's just for reading most of the time. So we're pushing a shared reference into the vec. So the vec now contains a pointer to the string. And then we print the vec. This exclamation point means that print is a macro. All we need to worry about is that means it can have a variable number of arguments. We don't have to get into any other details. This format string here could have any number of elements in it. In this case, it has just the one format specifier, and : means debug print. No big deal. So this is just a print. We don't have to think too hard about it. Okay? And we saw that it prints the list. As you can tell, I have some comments here foreshadowing what we're going to do to the code. So let's break this code. So the first thing we do is we can try to drop the string early. So instead of being destroyed at the end of scope, here on line 11, where the string normally would be, now it's destroyed on line 9. Rust calls that dropping. In C++ terms, this is where the destructor of the string would run. And Rust does not have a garbage collector. So we do need to worry about how long things live. And if we keep a reference to the string, as we have, past the point where it is destroyed, and we keep using that reference as we do, we have a problem, right? This is a problem. In C++ terms, this would be a use after free. Garbage collected languages don't usually have to worry about this, but we have to worry about it. Luckily, in Rust, the compiler will tell us about this mistake. So we'll save the code, back to the terminal, and run the code, and we get an error. So folks who have written, say, a couple hundred lines of Rust already have probably run into this, right? This is a lifetime error. It's not going to say lifetime because in the bodies of our functions, Rust usually just figures stuff out. That's true of the types, and it's true of the lifetimes, and it's not going to require us to think about lifetimes explicitly, but it can see that these lifetimes don't work out, right? The lifetime of the string ends here. When we drop it, we're trying to use a reference to it all the way down here. Clearly that doesn't work. Rust is going to say that we're trying to move the string. We think of it as dropping or destroying. Rust is going to call that a move. Similarly, we might think of this as a pointer or a reference. Rust is going to call that a borrow. That's just how the compiler is talking about it. But we understand this error. So we've done the illegal thing. Okay. So we don't do that. So if we comment that back out, this code works fine. Where we run into more trouble is when we try to do the same thing, but using helper functions. So let me go ahead and uncomment this helper function here. Right, so we're going to do the same push, but we're going to use another function to do it. And if you've written functions in Rust before, you know that you have to write out the types of the arguments. So these types are required. And what we're going to see is that we're also going to need to tell Rust some things about the lifetimes of these arguments, and I have not done that. So folks who've run into lifetime errors before might recognize this is going to be a lifetime error. Let me go ahead and write the function call. So my push. Now it's not a method, so we need to explicitly take the immutable reference to the vector, though previously the dot, the method calling dot push, was doing that for us. We do it here ourselves, my vec, and the same my string, right? And this code looks fine. It really seems like it's doing the same thing, and it's not going to work. Even though we've commented this out, we're not dropping the string early. It kind of should work, we might think. It's not going to work. Let's see it. So now we really have a lifetime error, right? It says lifetime. Okay. And it says a bunch of gobbledygook. And we can see a hint like, yes, this is ultimately how we will solve this error. We'll get there. But I want to spend some more time thinking about what we're seeing before we do. And there's, by the way, something especially surprising about what we're seeing here is if I go ahead and comment out this line, I'm not even calling the function anymore, right? So I've defined the function. I'm not calling it. It turns out we're still going to see the error. Let's show that. So we've got a warning about some unused code or unused variable. But if I scroll up past that, oh, it's the same error. Lifetime does not live long enough. So the error that we're seeing here really has nothing to do with main at all. In fact, I could comment out all of main and go back here and run it again. And now we see just the error. So this error that we're seeing is the same error we saw before when we were calling the function. This error is only looking at the function definition itself. It doesn't care how this function is called. It doesn't like the definition. So what it's going to end up telling us is that what we've said here in the function signature is not enough to do this, right? We're used to having to say the types, and it turns out that when we wanted to do things like this, we need to say more than that. We need to say something about the lifetimes. So we're going to get to that. Let me put my main function back. So this does not work. Instead of diving right into lifetimes, well, we're in lifetimes, but instead of diving right into explicit lifetimes, which is where we will go with this, I want to take a detour. And this might sound a little weird at first, but I think it's going to be interesting when we look at it. I want to look at what happens when we make my push take a T, take any type, not just a reference to a string, but any type T. So when we have generic functions in Rust, they look like this, similar to C++. And what I'm going to do, call it an experiment. What I'm going to do is I'm going to say this is a vec of T. It could be anything. So in a way, I'm telling the compiler less about this vector than I was before. Okay, so I'm pushing a T into a vec of T. kind of odd. What we'll see, and this I think is quite surprising, this works. This fixes the error. I think that's very surprising. Going back to the code. So by telling the compiler less, it certainly feels like we're telling the compiler less about the type. This type could be anything. We fix the problem. It's a little bit interesting, a little bit odd. It may not be too surprising that this works, because if we go to the documentation for push, I have that here in my browser already, I think. Yes, so this is the standard library documentation for vec, and here's the push function. And yeah, push works on a vec t that's at the top of the page, and we see that it takes an element or a value of type t. That's how push is defined. So maybe it's not too surprising that my push works, because it's almost a copy paste of the same definition. In a way, it had better work. If push works at all, this should work. But gosh, isn't this surprising? Like, it feels like we're telling the compiler less than we were before. Well, it turns out that in one specific way, we're telling the compiler more, right? In one specific way. And that is that we're telling the compiler that this type, t, and this type, the element, t, here we have, almost by accident, told the compiler that these are exactly the same. We've given them the same name. It kind of looked like we were doing that before. They looked similar, but it turns out we weren't doing that before. We'll see why in a minute. We've given these two types the same name. We've told Rust these are exactly the same. And it turns out that that is all Rust needs to know to make this work. So this relationship between my string and my vec and the reference that we take here and where it goes and the fact that it needs to live to here, all of that is somehow kind of encapsulated or, somehow contained in this idea of t. The type knows how long it lives or needs to live. And by saying that these are the same type, in the case that they are references, we're also saying that they live the same amount of time, more or less. That ends up making this work. Here's another surprise that I want to see while we're here. So again, if I try to run this code, we said this does work. If I try to drop here, this had better not work. It didn't work before, and it shouldn't work now. And it doesn't. That's good, right? So we've pushed foo into the reference to foo into the vec. We're not allowed to drop my string, the foo, while we're about to print it. That's good. That's not surprising. That's good. Here's the surprise. If I comment out this line where we actually do the push, if I don't push element into vector at all, it still doesn't work. This error has not changed at all. So Rust's view of what's going on in main, let me go back to the code. Rust's view that this line is illegal has nothing to do with this line here, with the actual place where we do the thing where we need this to be illegal. Rust doesn't care about this. At least when we get here, Rust doesn't care about this. It's not looking at the body. When Rust analyzes this code, it is only looking at the signature. This is kind of the mirror image of what happened before. Previously, when we first tried to write the myPush function, we saw that Rust doesn't like it, and it doesn't like the body, and it doesn't care how it's called. Now, we see that Rust doesn't care about the body, and it doesn't like how it's called. Sort of in both cases, Rust is sort of only looking at the signature of the function. Before, it only looked at the signature function of the function to see whether we could do this. Now, it's only looking at the signature of the function to see what the caller is allowed to do. So the signature is kind of like a barrier in some sense. The compiler doesn't look past it, either from the outside or from the inside. I think it's very interesting. I think it's very interesting to see that we still get this error even when we don't push. Last thing here, and then we'll go back to actual lifetimes. if we wanted to allow this, if we wanted to allow the caller to drop, well, then of course we can't push into the vector, but we have to change the signature beyond just commenting out this line. If we wanted this main function to work, we would have to change the types here. We'd have to say that element is not the same type as whatever it is in vector. So to do that, just as an example, we could add a u here. T and u are the typical names for type parameters. If we make this u, now we're not saying that these are the same type. And now, if we go run the code, we get a warning about some unused variables, but it works. And of course, we're not pushing the element, our string, into the vector. The vector is empty. This code works. So as long as we don't tell the compiler that this and the contents of this, that's this guy, as long as we don't tell the compiler that those are the same type, then no lifetime relationship is established. Everything's still free to do whatever it wants. We can drop the string here. It's not in the vector. Now this works. So this question of whether these are the same type really is the central question. And of course, now that we made them different types, we know we can't do this, right? Pushing a u into a vec of t, like obviously that's never going to work. And we can see over here, yeah, for sure, the compiler says, yeah, no, mismatched types, right? And this is clear. I think when we write t and u and we try to push a u into a vec t, of course that doesn't work. But the reason I bring this up is because I want us to start thinking about the lifetime errors as the same error, even though the compiler talks about it in a very different way. What's happening mechanically is very similar. We're trying to push a thing into a thing. We're trying to push an element into a vec. And the compiler does not know that the types are the same on both sides of that relationship. It talks about it differently, but it's the same problem. Okay. So let's get back to the code that we wanted to write. So of course we don't necessarily want this to be generic here. We want to treat it like a function that works with strings. So this was a vec of string, and our element is a ref string. It is a vec of ref string. So this is what we wanted. And we don't want to do the bad thing, right? We don't want to destroy the string. We're trying to get this code to work. We expect that this should be able to work. I want to remind us what the error was. Yes, lifetime. Okay, now we're going to go back and we're going to confront this, what the compiler is telling us to do here. So, but now we have a new perspective, right? We have a new perspective on this problem. Is that the compiler is seeing these types and gosh, they look the same, right? We've spelled them exactly the same way, but we know what's going on. Under the covers, there's something about these types that's not the same, or at least not necessarily the same. We haven't told the compiler that those have to be the same. There's some invisible extra stuff here, and that's the lifetimes. So before I write this out, I want to make a quick reference. There are rules for what happens when we leave the lifetimes out. Like we said before, Rust usually requires us to be very clear about the types of our functions. It's not looking at the body and figuring out what the type should be. And when we leave lifetimes out, that's still true. It's not looking at the body to figure out what the lifetimes we left out should be. Instead, it's following a set of rules that have a funny name. They're called the lifetime elision rules. That is, to leave a lifetime out is to elide the lifetime. Slightly fancy word. I have those here in my browser, I think. Let's see. Yes. So here is where in the Rust book, the official book, this is one of the chapters, goes into lifetime elision. Here's the same thing in the Rust reference, where it's a little bit shorter and more technical, but it's the same rules. And we can read this part of the Rust reference. We can see this rule right here. So each elided lifetime, each lifetime that is left out of a function signature in the parameters, on the argument side, we're not talking about the return value yet, but on the argument side, each lifetime that's left out becomes a distinct lifetime parameter. Let's just write that out and make it clear what that means. So there were 3 lifetimes in the signature here. There's 2 of them that we're paying careful attention to. And it turns out there's a 3rd one right here. We haven't thought much about that. It is there. So let's add 3 lifetime parameters. And like the compiler was suggesting, here's what they look like. So that apostrophe is, I call it tick A, tick B, tick C, or apostrophe A. That means this is a lifetime parameter. So it's kind of like a T. It is a type parameter, but rather than being a data type, like string, this is a lifetime. And we start putting them in where the references are. So let's put them in. So I'll put that one there. Put B there. And I'll go ahead and put C here. And for the most part, especially at the beginning, lifetimes only ever show up when you have references. There are other places they show up. You can have a struct with a lifetime parameter. Iterators tend to have lifetime parameters. That's a little bit more advanced. We usually don't have to write them. I recommend you avoid putting lifetime parameters on your structs, especially at the beginning. That tends to get pretty confusing. But for the most part, most of what we have to care about is references. They have a lifetime. And now we've written them out. So A, B, and C. So all we've done is we've gone, I would go back to the browser here. We've sort of undone this lifetime elision rule, and we've just written out what the compiler was already assuming. And the rule says that when we didn't say anything, they're all different. Here on the argument side, we don't have a return value. So I'm not going to talk about the elision rules for the return value. There's a couple more of them. We're just talking about the arguments right now. So we've written it out, but we haven't changed anything. So if I save this and run it, we still see an error. Right? It's talking about the error differently. Okay. And it's making a very different suggestion. We're not going to do that, but we'll come back at the end and talk about what that means. That's different. We're not going to do it. But at least we have names. And now we can go back in here and we can think, okay, we've seen this problem before. We know what the issue is. In fact, now we can see the issue, right? These things need to be the same type, just like with vec_t, right? So what we have here is basically the same thing we had when we had my push of T and U, right? So here's T and here's U, and they're different, or at least they can be different. And they have different names. Now we've said most of it. We've said it's a reference to a string, but there are parts of them that are different. Same issue, right? It's a type system issue. And I think now, even if you hadn't seen the hint, of course, now we've all seen the hint, but even if you haven't seen this before, now you can probably guess exactly what we need to do. We need to give these the same name. So I'm just going to call this A. And if I save that, so one character change, this B became an A. If I save that and run it, boom, it works. So by writing out the lifetimes, we sort of gave ourselves a place to fill in the missing information about the types. What's the same? We stopped using B. The compiler doesn't seem to care, but I'm going to go ahead and delete it since we're not using it anymore. And I'm also going to delete C. So we've given this lifetime a name, but we haven't used this name C anywhere else. So its name kind of doesn't matter. If we haven't said anything about it, it doesn't have to live as long as anything else. And we actually know this had better be living not very long, the ref mute to the vec, because mutable references in Rust have to be unique. So that had better not live very long, because we want to keep referencing the vec in other ways. So we have not established any requirements on C. So that is the same as just not giving it a name at all. And we can delete this. And now we've arrived at exactly the code that the more experienced Rust programmers would probably have written. It's what the compiler suggested for us, right? We've only needed to name one lifetime parameter. We've left this one unnamed, and we've said that it's the same in these cases. And now the compiler's view of the types lines up. It believes that this is legal, right? And here in the caller, right, it knows that let's run this code. Again, we can remind ourselves this works. This is valid. If we uncomment the drop, if we destroy that string too soon, this shouldn't work. We expect this to fail. Yep. Exactly the same error as we saw in the beginning when everything was in main, right? The string is borrowed. We can't destroy it. Good. Expected. And hey, we can see the same thing we saw with T and U. If I go up here and I comment out the body, same as it was before, this is still illegal. We go back here, we run it. The error hasn't changed at all. A warning about an unused argument there, but the error hasn't changed because same as with T and U, the compiler's only looking at the signature when it decides whether what the caller is doing is allowed. So that's the story here. That's how we wind up. Let's get rid of the bad code and add back the good code and run it one more time for good measure. That's how we wind up with the explicit lifetimes that we have here. Before I end the story, I'd like to mention there's a mistake we could make here. So you might make this mistake when you're learning lifetimes and experimenting and trying to figure out where they go. We could have put A here also. And we shouldn't do that. Because if we do that, we're saying this mutable reference to the vec has to live as long as the contents of the vec. So this mutable reference to the vec has to live as long as the vec lives, till end of scope here. That's not going to work because Rust has the no mutable aliasing rule, right? Mutable references have to be unique. So if this is going to stay alive, we're going to run into trouble the next time we try to reference the vec. That's going to be an aliasing violation, and we can see that. Right? Cannot borrow my vec as immutable. That means as shared. Cannot borrow my vec as immutable because it is also borrowed as mutable. We violated the mutable aliasing rule. And again, there's nothing wrong with this code, but here in the type signature of my push, we said the wrong thing. We told Rust the wrong thing. And that makes Rust think that this code is illegal. So we have to not tell Rust that reference lives as long as these things. We have to leave it unconstrained. It is free to live for a shorter amount of time. Even though of course, it's not the same type. This is a mutable reference to a vec. That is not a shared reference to a string, but we still have to avoid saying that its lifetime is the same. Right? So that's a mistake that you can make. I'm sure we'll all have many chances to make that mistake over time. For completeness, there are some fancier details of the borrow checker lifetime type system that we have not covered here. We did see one of them. So when I had B here, and we called this B, this is wrong, right? Because we haven't said that they live the same amount of time. This line will not work. When we had this, or something like this, we saw that Rust gave us this suggestion. This is a little fancy. That's not usually how we fix this, but we could. This is what's called an outlives bound. So we could put this somewhere. There are a couple different places you could put it. And this would say that B outlives A. It's not the same as saying that B is exactly the same as A. It's saying a little bit less than that, or it's saying something different than that. This is a little fancy. You're not going to need it. So when you get around to reading the Rustonomicon or whatever advanced sources, you can learn all about this. You can see some examples in the standard library where this is used. For now, I'm going to say you don't need it. 99% of the lifetime problems we see as we're learning Rust, all we need to do is tell Rust that two things are the same. We don't need the fancy thing. Also, for completeness, there are other rules for how sometimes a thing that lives longer can be used in a place that needs something shorter. Rust calls this variance. You will see variance if you go reading the Rustonomicon or other sources. It's interesting, it's a little bit complicated, and we don't need it. So I just want to be honest that we're looking at a subset of the rules. We've already seen plenty. We've seen what lifetime parameters look like. We've talked about the elision rules for when we're allowed to leave them out. That's good enough. That's good enough for your first couple years, probably. The more advanced stuff, when you start writing libraries, or reading library code, you can reach for that. There will be a time. So this is Rust Lifetimes. I hope the next time you run into these errors, it feels a little bit more like you know what's going on and why you need to say the things you need to say. There is method to the madness. There are rules. The compiler does follow them. And I think understanding them is pretty fun. So thanks, everybody.